Good morning, one and all. Let's start our keynote address session. So, the session chair is Dr. Krishna Mohan Kovan. Dr. Krishna Mohan earned his PhD in software reliability with applications of artificial intelligence from IIT Bombay, India. His expertise includes artificial intelligence, quantitative risk assessment, and software reliability engineering, with a focus on applying research to real world areas such as healthcare, agriculture, banking, industrial automation, and public policy. He currently serves as Principal Data Scientist at the University of Alberta, Canada, Chief Innovation Officer at Banking Labs, Board Member at Metabolomics, include INC, and advisor to several startup ventures. He also holds an international faculty position as professor at Manipal Academy of Higher Education, MAHE, India. Earlier, he worked as research review consultant at Metax, Canada. Evaluating university industry research projects, he is actively involved in academic publishing as an associate editor for Springer Journal and series editor with CRC Press. And the speaker of our today's session is Professor Rajesh Karki. Dr. Rajesh is a professor in the Department of Electrical and Computer Engineering at the University of uh, Saskatchewan in Canada. He leads the Reliability Research Lab in the Power System Research Group. He is a fellow of Engineers Canada. He specializes in the area of power system reliability and value based reliability investment with over 30 years of experience in research, application, education, and consulting work for electric power industries and academic research institutions. His research includes renewable energy storage, smart grid initiatives, and electricity market implications on the environmental compliance, efficiency, reliability, and resiliency of power systems. He has published over 150 technical papers, 5 books, many book chapters, and technical reports in this field. Now I request Professor Rajesh Karki to present his paper or his presentation.
Thank you for the introduction.
Good morning, sir.
Good morning. Can you hear me?
Yeah. Yes, sir. Sir, how are you, sir? I am Krishna.
Oh, hi. Good.
Yeah.
I'm very good. How are you?
I am fine, sir. I think it's 9:30 for you. 9:30 p.m. in Canada now.
No, actually, I'm in eastern part of Nepal. I was attending a conference there.
Okay, okay.
So then, yeah. So
Yes.
I'm from there right now.
Yeah. Sir,
So the timing is good for me.
Oh, great, sir. Yeah. I'm also in India now, so yeah.
Okay.
I came from guest assignment at MIT, Manipal. And yeah, you hear I'm here for the conference. Yeah.
Well, it was nice really getting in touch with you here.
Right, sir. So, sir, we welcome you for the keynote address, sir. Please start, sir.
Yes, thank you.
Thanks.
Yes, thank you, Mr. Chair, distinguished guests.
So, just
sorry.
Okay, you may start, sir. You may start.
Okay. So the title of my talk today is Emerging Trends of Energy Needs for Sustainable Development. And then my talk really focuses in the value-based reliability investment challenges in order to provide that energy needs, in order to minimize the overall societal costs. Yes. Sorry. So we all know energy is needed for economic growth. Economic growth can be stalled if there is no energy. So there is a very strong relation between energy and economic growth. So energy is needed in order to induce economic growth in any country or in any jurisdictions. So when there is economic growth in a country, that brings prosperity in the society, and with prosperity there is increased energy consumption. So this is like a cycle. You need energy for growth, economic growth, which brings prosperity, and with prosperity that increases the energy needs. So here I have a figure which has GDP per capita on the x-axis and electricity consumption per capita in the y-axis, and there is almost a linear relation between the two. So obviously, there are no energy rich. Like if you are low on energy, obviously those countries cannot be rich. So you need energy to become a rich country. So that's the overall message from this figure. Now, energy. So we talk about sustainable development. So therefore, that means maintaining a long-term balance between environmental protection, social equity, and economic prosperity. So this environmental protection is key to energy generation and energy consumption while we target sustainable development. But we all know the global warming is a major concern, which is believed to be due to the reason of greenhouse gases. And on the left side, the top pie chart that shows the sources of greenhouse gas emissions. And from this data, you can see that about 76% of that is contributed from that is related to energy. And zooming into this energy, the lower pie chart shows that more than 42% of contribution comes from generation of electricity, and more than 22% is from the transportation sector that consumes gasoline and various types of petroleum products. And obviously, there's a home heating, 8%, and so on. So therefore, there is a global initiatives or some sort of global understanding to take steps to offset emissions and to reduce this greenhouse gas effect. So for the electricity generation portion, there is various types of promotion for renewable energy resources, and for transportation sector, replacement of petroleum fuel to electric vehicles, and in countries like Canada, where it's very cold, home heating is a major source is a major energy consumption. Currently, mainly from natural gas, that needs to be converted. That is gradually being converted into electric home heating. So we can see there is a growth in energy needs, and we can separate that into two sections. One is the conventional load growth, which mainly due to population growth, economic growth of a country, which requires energy. So there is this. So this causes when I say load, that means the demand for energy. So there is this has always been there. The demand for energy from these two sectors. Uh, and then obviously with economic growth, I had mentioned that earlier, when you get prosperity, that you tend to consume more electricity. For example, instead of washing dishes with hands, you want to wash that with a dishwasher and laundry. So everything eventually becomes converted into electricity consumption, and that increases the growth with prosperity. Now, there are also some new trends that are happening that causes a significant amount of increase in demand, energy demand. And one such factor is the AI revolution. So this is considered, or this is recognized to be one of the major sector for energy growth for the next decade or so, because we require lots of data centers all over the world, which has significant energy demand. And another new trend that we see, as I mentioned earlier, are these decarbonization initiatives. That means offsetting conventional fuel with electricity, such as electric vehicle growth and home heating from electricity and so on. So this is also going to be a significant increase in energy demand. So the data center energy requirement is believed to be the primary, the major amount of energy that is needed in the next decade or so. And then electric vehicle is the next one. So this growth in energy from these sectors are going to be much more pronounced than the conventional load growth we've seen over the years. So, so in summary, so these emerging trends of energy needs is going to cause a significant growth in electricity demand. And how do we meet that demand? Because in order to meet that demand, we need to produce electricity from renewable resources or resources that do not produce uh, emissions. And we know many countries have set a net zero emission target for electricity generation. So this is a big challenge, a huge demand to be met from resources that do not produce any sort of emissions at all. So then we need to decide where to invest in order to sustain this energy growth. Uh, the resource adequacy. Adequacy is another term related to reliability. So So there are reliability standards, reliability criteria that mandate adequate investment in electricity. So in order to provide reliable power to consumers, if adequate investment is not made uh, in electricity generation, then obviously there's going to be poor reliability, which causes excessive power outages, and therefore that increases the outage costs to the customers, and also lack of electricity causes the stall or lack of growth, lack of economic growth, and so that's a big problem. So we need to invest in electricity generation in order to maintain a certain level of reliability, so that we minimize the power outages. So I have on the plot, on the left plot, you can see x-axis I have reliability and y-axis is investment cost. So if you want to increase the reliability of the energy sector, of the power system, electric power system, you need to invest into the system, into the generation resources, and also into the transmission grid and so on. And by doing so, you improve the reliability. But this relation is not a linear relation, as you can see. So if you look at towards the left, the bottom left, if the reliability of the energy sector in any country is quite low, then even a small investment shown on the y-axis can produce a large improvement in reliability. But if the reliability in any country of power sector is relatively high, then in order to make the same amount of increase in reliability, that requires a significant amount of investment. So therefore, this is a really the judgment for investment to improve reliability really has to be done from quantitative reliability analysis methods. Now, when in these investments are made in to improve the reliability, who pays for that? It's obviously the customers, because any investment that is made into this is transferred to the customers as electricity price. So on the right side, I have another plot there, and in that plot, I have shown that same that blue line, which is investment cost versus reliability, but then I've added two other lines there. So if you follow that blue line from left to right, that shows that as you increase investment, the reliability improves. But then if you look at, and then that investment cost is obviously paid by the customers as electricity price. Now if you look at the red line and go from on the x-axis, you go from right to left. That means as the reliability degrades, that red line is outage cost due to power outages. You can see that the cost due to power outages increases as the reliability degrades. Okay, so who pays for that? Obviously, the customers pay for the power outage costs. So the customer pays for both, for the investment costs and also for the investment costs to improve reliability, and also the red line, the power outage costs due to lack of reliability. So therefore, if you add the two, you get that green line, which is the total cost. We call that the societal cost, which is on the customers. So therefore, we want to minimize that societal cost. So the minimum point should be the target reliability for any jurisdiction. So this is what we call the value-based investment for reliability in order to minimize the societal cost. So when we talk about reliability investment, more than 90% of that investment in any power utility, in any electricity power utility, more than 90% of the investment is in the generation resources. And then less than 10% is the transmission and distribution networks. So any investment in generation really affects the electricity price. So therefore, we need to make sure that we don't overinvest and also underinvest. So we need to know the right amount of investment. So this right amount of investment is perceived to be obtained when we just meet that reliability planning criterion. So you can see that obviously the generation in any country, the total generation capacity must be greater than the total demand by a certain capacity reserve, because the generation plants can fail, and if the generation plant fails, we still want to be able to provide the needs of the customers. So therefore we need that capacity reserve. So this capacity reserve, as you can see, is the minimum when the demand is at the peak. So therefore, so at the peak demand, the minimum when you have the minimum reserve, that minimum reserve helps maintain reliability in the event of component failures, generation failures, transmission failures, and so on. Okay. Now, in the conventional energy system, we have the conventional energy demand profile. We more or less know what the demand variation profile looks like, and therefore it was pretty, and there were established methods to figure out how much investment is to be made, and there were probabilistic index called loss of load expectation, LOLE, as the planning criterion, which says that the power outage probability should not be less than 0.027%. So this is in the industrialized countries. Okay, so when you meet that criterion, then it is believed to provide minimal societal cost. But when we have this now looking into the future trends, this future energy demand, emerging loads such as electric vehicles, and conversion of home heating from natural gas to electricity. So with that, because this demand really also depends on the weather conditions. So with weather variability, these demands tends to vary. So there is more variation, more uncertainty. So we can see that in this figure, if these emerging loads were not there, then only with the conventional type of load. So on the right side, I showed that is the amount of minimum reserve in any system. But as we now increase the emerging loads, such as the electric home heating, there is less reserve now left into the system. And with electric vehicles, that reserve even reduce is even less. So therefore, that what that tells us is there needs to be more investment into the capacity reserves in order to maintain the same level of reliability, to minimize the societal costs. But then these reserves are harder to predict because of the increased variability. As you can see here on the left side, I have shown wind power on the y-axis and then time on the x-axis for 1 day. So this shows a diurnal variation of wind power. In this is from a Canada Saskatchewan data. That's where the University of Saskatchewan is, and you can see this is an average data. The lower one, the black one, is for the summer season, and the red one on the top is for the winter season. The winter we have colder season, so there's less. There's more dense uh, air that produces more energy. So this variation, there is a diurnal variation as well as there is a seasonal variation in wind power resource. And this is true for the other jurisdictions, other countries as well. On the right side, I have shown the solar power, photovoltaic power, the winter and the summer, what they look like within for 1 day. So summer has longer days and more sunshine, so you can see there's uh, uh, more energy, whereas winter has less energy. But we get more conventional demand in the winter time, but less resource output from the sun in the winter time. So all, and because these are all dependent on weather, so when we try to do our evaluation and create reliability models, we have to take into account the cross correlation between their variability and their interdependence. So if you look at this figure here, the black curve at the top shows the demand for power on a typical day. So the demand within a day is not constant; it varies. At the night time, the demand is very low, and then during the daytime, it slightly increases, and in the evening time, it kind of peaks, and then again it goes down. So the peak demand is the time when a lot of generation is needed. So when we talk about investment in generation resources, that those resources must be able to produce power to meet the peak demand plus some reserve over the peak demand. But if you look at the renewable resources, you can see that the solar, no matter how much you invest in solar power, it will not contribute to meeting the energy requirement during the peak time because that occurs during the evening time. So solar has zero value in terms of meeting the reliability to minimize the societal cost. And for wind, you can see sometimes there may be some wind power, sometimes there may not be wind power. So if you take the expected value of wind power during the peak hours, those are pretty low. So the challenge here is we need renewable resources for sustainable development, but then they have very little value or no value to meet the demand when it is most needed. So therefore, that causes a reliability concern. And if there is lack of reliability, there are more outages to the society. So then the societal cost is not minimized. That tends to increase the societal cost. So therefore, in this case, the energy storage systems come into play. So there is a huge market for energy storage system. And so now, how do we coordinate energy storage in the evaluation process is another challenge that me and my group at the university are currently working on. So I can notice that my time, I think, is up. So I do have some more slides here. I think I'll just end here. Thank you very much for giving me this opportunity to make this presentation. Thank you.
Thank you very much, Dr. Rajesh Karpi. Any questions from the audiences?
Sorry, sir, actually you mentioned somewhere societal cost, right?
Mhm.
Sir, how do we mathematically calculate that?
Thank you for the question. It's a very good question. Yeah, the societal cost. So in this value-based reliability investment approach, as I mentioned, the customer mainly sees two types of costs. One is the costs for investment into the system, uh, such as investment in generation facilities, which is again transferred back to the customers to pay as electricity price. And then there is this outage cost. So when there is an outage, there is a cost to the customer. So you combine both of those costs, and we call that the societal cost. The first part, that investment cost, that is very easy to calculate. So you know what you invest in, and then you know the price of those things, and then you take a 20-year life of those infrastructure or those resources, and then you can make the cost per year or so. But the outage cost is not that easy to assess. But when we say customer, there are different types of customers. There are industrial customers, commercial customers, residential customers, farm customers, and so on. For industrial customers, this outage cost is relatively easier to calculate, because you can say, if there's a power outage at a certain time, certain season, then the industry can figure out what would be the cost to them when there's a power outage during that time. You still have to pay the workers. There's no production, and the production is stopped. Maybe they cannot meet their deadlines, and there might be a penalty for not meeting deadlines, and so on. So these costs are relatively easier to calculate. But there are costs such as uh, for residential customers, if when there is a power outage, maybe, for example, you are studying for exam, and so that hampers your exam results, and that hampers your future. So there are non-tangible costs, and we struggle to really put a monetary value to that. So uh, we can only put a guess to those values. We have to rely on economists for those values. Uh, but you're right. These costs, and also the there are costs due to power outages. There are costs for lack of opportunity to make an economic growth, economic development. So how do you put a monetary value to those costs? So there's still quite a wide area for research, mainly from the economics or commercial researchers into this area, which we don't really have that much expertise to do that, but we just kind of rely on estimated figures for this. So if we can include all these monetary values of all these non-tangible costs, then the outage costs will be much higher than what we're estimating right now.
Okay, sir. Thank you, sir. Hello, Professor Kaki. This is Kapoor here.
Hello, Professor Kapoor. Good to hear your voice.
It would have been good that you could come physically to the conference.
I know. I really have to apologize.
So next time when we do it, please do come.
Sure. Okay. I promise for the next time.
Thank you very much. And I came late to your lecture, but it was nice. But we also in software, we have when to release a software.
Mhm.
It's a very difficult question to answer. So we have several costs.
Mhm.
Costs which are time independent. So that's also a problem. Can we have costs with time dependency?
Mhm.
So what is the nature of those costs and all? Still, the $1 million question in software reliability. But it was nice hearing you. Thank you very much. Thanks for your
Yes. Thank you, Professor Kapoor. Yeah, we do have that issue too with time, because if outage occurs at a particular time versus another time, the costs can vary quite significantly. So yeah, there is actually a lot of opportunity for interdisciplinary research, and I see your seminar is quite interdisciplinary, and I hope we have audience from the expertise in the other fields that can really help improve this area of research as well.
interdisciplinary research department. I'm heading that.
Mhm. So yeah, that is very important in today's research world.
All is well. Everything is fine.
Yes, Professor Kapoor. I'm heading out to Japan next week, so there was just too much travel at this time.
Well, okay. Thank you.
Yeah, thanks.
Okay, thank you so much, sir, for such an insightful presentation. Now, I would like to request Professor P.K. Kapoor, sir, to felicitate our session chair, Dr. Krishna Mohan, sir.
So let's begin with our next keynote address. Our session chair is Professor Deepak Kumar sir and speaker is Dr. Vidyashi Nagaraju ma'am. Dr. Deepak Kumar sir is a professor at the Amity Institute of Information Technology, Amity University, Noida, and a visiting professor at Fayetteville State University, US. He also serves as the head of student research and project, and he completed his MTech in computer science from BIT Misra and earned his PhD from the University of Delhi. He has received several recognition, including the Young Scientist Award and International Award for his contribution to software reliability engineering. He serves as the editor-in-chief of the International Journal of Science and Informatics and holds editorial roles with several reputed international journals and book series. Dr. Kumar has authored a book on software reliability engineering, published more than 150 research papers, filed 9 patents, and guided multiple PhD scholars. He is also a fellow and senior member of several professional bodies, including IETE and IEEE, and has delivered invited talks at leading universities worldwide. Vidyashree Nagraju earned her PhD in electrical and computer engineering from the University of Massachusetts, Dartmouth in 2020, and she is currently an assistant professor in the Department of Electrical Engineering and Computer Science and has worked as a senior safety and reliability engineer on aerospace and defense projects since 2022. Earlier, she taught at Stonehill College and the University of Tulsa. She has published 50 plus research papers and on reliability modeling and algorithms in the journals like IEEE Transaction on Reliability and the Journal of Risk and Reliability. She also received the 2020 from uh, Tom Fagan Student Paper Award from the IEEE Annual Reliability and Maintainability Symposium. Now I request Dr. Vidyashree Nagaraju ma'am to start with our presentation.
Welcome, Professor Vidyasiri.
Ma'am, you need to unmute yourself. Ma'am, you can leave and rejoin. I think it's some microphone issue. You can just rejoin.
Hi, can you hear me now?
Yes, ma'am, you're audible. You may now
Perfect.
share your
Let me go ahead and do that. Let me know when you're able to see my screen, please.
Yes, ma'am, it's visible. You may start.
Perfect. Thank you. Excuse me. All right. Sorry, give me just a moment. I don't think my screen is advancing. There's something going on with the Zoom connectivity here. Pardon me just for a second. All right, here we go. I hope you all can hear me and see me. Good morning, and thank you for this opportunity to be here and speak with all of you. My name is Vidishri Nagaraju. I'm an assistant professor at the Embry-Riddle Aeronautical University. I'm currently in the systems engineering department with a focus on software reliability and safety as well as security. Today I'm presenting a hybrid LLM SRGM framework, the large language model software reliability growth model framework for artificial intelligence enabled reliability assessment in safety critical software systems. The motivation is pretty straightforward. Safety critical programs need reliability evidence that is both quantitative as well as interpretable. And the current reliability modeling practice struggles to keep up with the scale and complexity of these modern verification workflows. The key premise is that we already have the missing context, right? Like such as severity queues, subsystem interactions, the debugging effort, as well as, all these things are embedded in routine engineering text because we are always pushing the code, adding comments, we have developer notes, we have so much documentation, and the way we...
Your PPT is not visible. Kindly share your PPT also.
I think I am sharing, but let me go ahead. Stop share. I'm going to try that one more time. Can you see my screen now?
Yeah, it is visible.
Okay. All right. All right. So as I was mentioning, the whole severity queue, subsystem interactions, and all that information that's embedded in these engineering text through developer notes, as well as the way we would debug, as well as, test engineers, verification, validation engineers. So we have a lot of data, a lot of content. One of the biggest challenges that we talk about in doing software reliability is not just the modeling or the approaches, but also the availability of data. It's not just the quantity of data, it's the quality of data as to what do we extract, what is important, what is not, what should we focus on. Sometimes when developers or engineers are marking some information, they may classify high severity information as a low severity. And when we talk about safety critical, mission critical systems, being able to misclassify something such as this through human error would also become an issue. But as humans, as we are scraping through this data and trying to pre-process or translate this data into a reliability model compatible data, so we can do all sorts of assessments and metrics, we just tend to go with the text, whereas using AI-enabled approaches will help you identify those correlation and the interconnectivity to be able to say, hey, yes, this was marked as a low severity, but based on the way it has been resolved, this is actually indeed a high severity, which would have a catastrophic consequence if we hadn't resolved it, or it could lead to a bunch of other bugs, right? Anyway, so the question is, how to extract it systematically and bring it into reliability assessment without discarding the whole mathematical structure that the software reliability growth models and non-homogeneous Poisson process models provide. Here is the roadmap for the talk. I'll start with the motivation and background, why software reliability assessment remains a persistent challenge in safety critical systems, and what these models do well today. Then I'll describe the gap. Traditional models largely consume defect counts and timestamps, while verification and validation produces rich, unstructured artifacts that are really hard to process manually. And after going through that, I'll walk you through the proposed hybrid framework. I'll mostly emphasize on the LLM side of work instead of going into SRGM, which is a whole another can of worms that we don't want to get into today. And the semantic extraction methodology and an illustration using synthetic aerospace defect dataset, ending with conclusions and future work. Introduction, software reliability assessment. It's really mission critical in aerospace, defense, transportation, healthcare, energy, you name it, because as we've been talking about it, failures can have severe consequences. We could lose a lot of lives, we could lose a lot of infrastructure, there could be a severe economic damage. So historically, these software reliability growth models, or SRGM in short, provide a mathematically grounded way to estimate defect discovery behavior during testing, often using an HPP formulation where the expected cumulative defects, M of T, grows over time. At the same time, we have large language models, or LLMs in short. They have become strong at interpreting technical text and producing structured outputs. And that matters because modern verification and validation, or V&V in short, generates huge volume of artifacts, right? Logs, anomaly reports, test narratives, code review notes that contain reliability relevant semantics. So the opportunity is to treat those artifacts as data, not just documentation. That's the focus of, or the motivation for this work. The challenge here, this slide makes this gap explicit. Safety critical systems, they generate vast unstructured artifacts. The traditional reliability models mainly use numerical failure counts, right? That means they treat faults as statistically equivalent, even though engineers know severity, subsystem coupling, and recurrence, all these behaviors matter. Mathematically, non-homogeneous Poisson process software reliability growth models, which is a mouthful, or NHPP SRGM in short, they track aggregate trends, but they typically don't condition on context unless we supply structured covariates. Extended models do exist, such as covariate models incorporating change points, imperfect debugging, as well as utilizing different learning algorithms. But they require inputs like labeled severity, change points, effort measures, things that are often missing or inconsistent in real programs, right? So the practical limitation isn't the math, it's the lack of structured, trustworthy context at scale. So our proposal is a hybrid framework that integrates these large language-based semantic extraction with our NHPP-based software reliability growth models. The point is not to replace SRGM, but to augment reliability assessment with context that is already present in engineering text. In reliability terms, we still observe defect discovery over time, but we are simply going to enrich each defect event with attributes like severity or subsystem recurrence and integration markers. And this supports enhanced predictions, better interpretability, and earlier risk identification, especially around defect classes and testing phases where reliability behavior changes. And this is extremely important, even being able to extract the information based on subsystems, because when we start looking into all these safety critical systems, we start narrowing down our focus towards components that are safety critical. In meaning, if anything were to happen, or if those components or functionalities were to fail, you're going to have a failure that could lead to a safety related issue. When we say safety, it could be personnel as well as equipment or infrastructure. So the hybrid framework architecture, this slide essentially shows the unstructured to a structured pipeline. It's a very simple process flow, just being able to preface LLM so that we have a better data assessment or data extraction here, right? So we begin with these textual artifacts from testing and verification and validation. So we ingest and normalize them. and we consolidate multiple records into a coherent narrative per defect aligned to a timestamp. So then the LLM extracts a fixed set of semantic attributes and outputs structured records. So the structured attributes become inputs for your analysis alongside classical SRGM. A helpful way to describe this transition orally is, instead of only modeling the time series TI in our software reliability grid model, we're going to model paired observations like TI AI, where AI becomes your semantic attribute vector. In this slide, we define the 8 contextual dimensions that we were looking at in our initial study. We looked at severity, fault class, recurrence, subsystem, fixed complexity, test phase, integration marker, and confidence. And these correspond to factors reliability engineers already care about, but that are usually not encoded in the data available to software reliability grid models. From a modeling perspective, these attributes can be used for stratification, change point detection, or as covariates in intensity-based formulations, right? Even without immediately rewriting the software reliability growth model likelihood, they substantially improve interpretability because, the shifts in your lambda t, which is d of derivative of mean value function m of t over t, can be associated with specific semantic drivers like integration events or clusters of critical defects. This slide summarizes validation results using a basic GPT-4 turbo model with a structured extraction strategy. The key takeaway here is that severity and recurrence are extracted with high agreement and consistency. And the subsystem attribution is also strong. It's important because these attributes tend to drive meaningful differences in reliability behavior. I want to emphasize what this means operationally. We don't necessarily need fine-tuning or heavy labeling program to get useful structure out of these defect narratives. And because a confidence score is included here, we can route any ambiguous cases for selective human review rather than forcing a fully manual pipeline. So we don't have to do it completely manually, or we don't have to fully automate it. If we are doing that confidence score for these LLMs, and if it's lower, you can always bring a human in the loop. For the sake of illustration, we use a synthetic data set that was designed to mimic realistic aerospace verification patterns across 5 integration windows over a 320-hour campaign. And this data was basically generated based on some of the real data that we have on campus. It's an aeronautical university, and we have quite a bit of resource in terms of commercial as well as defense flights. And so we collect significant amount of data with several organizations, as well as, we have a fleet of 150 flights right on campus and lots of UAS and drone facilities to be able to collect the data. But just for the sake of illustration here, we created a synthetic data set that would mimic this realistic aerospace verification patterns over a 320-hour campaign. The data set that you see here totals 140 defects, with a severity distribution skewed towards minor defects, but with meaningful critical clusters. The key is that the data are generated with realistic temporal non-stationarity, so that there are, regime shifts aligned with integration activities and phase transitions. That gives us a controlled environment to ask, when we add semantic attributes, do we recover structure that would be hard to see from the cumulative defect curve alone, right? That's what we're trying to answer here. In this slide, we quantify informational value via an ablation study. Severity contributes the most, as you can see here, followed by integration markers and subsystem, and together capturing the majority of structural signal in the dataset, right? Even relatively coarse semantic cues extracted automatically with imperfect accuracy can explain a large portion of the organization in defect behavior. In other words, you don't need a perfect extraction to gain substantial interpretive leverage over the reliability growth process. This slide shows that integration markers reveal phase transitions in defect discovery behavior. Critical defects concentrate in particular windows associated with the system integration and interaction, while these major defects cluster in stress testing and acceptance windows. That's where they appear, right? And mathematically, you can frame this as like a piecewise or a regime switching behavior and intensity, that your lambda t function, where change points indicate shift in test activity or system reconfiguration. The important point is that the regime changes are being inferred from semantic content rather than from structured phase annotations, which is exactly the kind of missing metadata problem this framework targets. Subsystem associations here reveal distinct severity profiles. Navigation shows the highest proportion of critical defects, consistent with the algorithmic complexity and sensitivity to interface discrepancies, right? And thermal shows the lowest critical proportion, consistent with more mature routines and limited cross-module interactions. Subsystem level profiles, doing it this way, they support targeted verification investment. So now we can focus our efforts on maybe removing this critical faults from the navigation system if that's your safety critical component. You can allocate your resources based on what's deemed as high risk or high failure, depending on your safety critical and mission critical classification. In modeling terms, you can think of conditioning this reliability growth on subsystem, essentially effectively analyzing different mean value functions for each of these subsystems or different parameter regimes across architectural components. Recurrence indicators extracted from the text provide a signal for imperfect debugging and the fixed durability, right? Recurrence clusters late in the campaign and are disproportionately critical, suggesting that high severity issues are more prone to incomplete remediation, right? In reliability growth language, it implies that defects found does not necessarily equal defects removed, and that effective remaining fault content may not decline as smoothly as aggregate curves suggest, right? So even if you don't explicitly fit an imperfect debugging model, recurrence helps explain why defect discovery may persist or spike after integration events. This slide addresses practicality throughout throughput, cost, and confidence distribution, essentially. The extraction rate supports continuous processing, meaning you can update semantic profiles as defects arrive rather than doing one-off analysis. The message here is that this is operationally feasible. You can integrate this as a lightweight service in your verification and validation pipeline. You can feed dashboards and support reliability reviews in essentially real time, because we're all headed towards real-time assurance, right? And while using these confidence thresholds to make sure we keep humans in the loop, only where the model is uncertain. So we're not blindly trusting all the models. So the conclusion is that LLMs can extract structured semantic attributes from unstructured defect narratives with sufficient fidelity to reveal meaningful patterns in verification data. Severity stratifies discovery dynamics. We know that subsystems show distinct profiles, and integration markers that we talked about, they reveal shifts in these processes and testing and verification and validation phase, all of which materially improve the interpretability beyond just using the defect counts alone. So in the future work, we are focusing on real program validation, as well as multimodal integration with other evidence sources like test coverage, code changes, as well as domain adapted, or even using RAGs, the retrieval augmented approach, to improve extraction fidelity, because several of these organizations, they operate under confidential data agreement, and they don't want to share data. They don't want to put the data outside of the organization. So using retrieval augmented kind of approach makes sense for those organizations to even demonstrate how to use that. And the broader point is that, this is a path toward reliability assessment that remains mathematically grounded while becoming much more context aware. I'll close this by inviting questions and discussion on two dimensions. First, the modeling side, how teams would prefer to incorporate semantic covariates into reliability models practice, right? And second, on the operational side, how do we integrate this into defect workflows without adding friction? If helpful, I can also discuss what would be required to move from the illustrative analysis to a fully parameterized covariate NHPP model in a program setting, including uncertainty propagation from extraction confidence into reliability estimates. With that, I'm gonna pause here and take any questions you may have.
Thank you, Dr. Vidyasri. So you presented a very nice presentation. So some questions from the audience also. So yeah.
Thank you, Vidyasri. I'm Krishna Kaur from University of Alberta. Do you have used any prompt engineering here in terms of prompt for LLMs?
Did we use what? I'm sorry?
Did you use any prompt engineering here for prompting LLMs?
We did. Just for the initial, we did use prompt engineering, but I did not go into that level of detail here. The article that follows through, we speak specifically about how we configured prompt engineering and some of the words that we used and the way we fine-tuned the model. But I intentionally skipped that because the focus was more on LLM. But to answer your question, yes, we did, and we are continually evolving and improvising on the approach that we were using based on different databases that we're exploring at the moment.
Okay, you said that you use like synthetic data points, right? So, do you have any real points, like based on the real points you have generated synthetic points?
Absolutely. So, like I was saying, we are at a aeronautical university, and right on campus we have about 150 flights that we use for the sake of learning and research, and for pilot training. And we have a lot of centers associated with aviation, as well as a lot of even students. They just keep playing with swarm UAVs and whatnot. So we have a lot of data, and our initial assessment in this model has been essentially focused on working on that particular data. But we're still getting through getting some approvals and clearances to be able to release results based on this particular data, especially because of the sensitivity of the project that we were working on. Hence, for the sake of publication and presenting it in venues such as this, we ended up creating a synthetic data, which was kind of mimicking what we had in reality, but just a part of it and just kind of normalizing, so we're not giving away the data that we're not supposed to until we get the approval. So to answer your question, yes, this work is being developed as part of a real project, real data. But for the sake of presentation here, we had to create a synthetic data just until we get some approvals and green lights.
Okay, ma'am. Thank you very much. Yeah.
Thank you.
So, any question? Dr. Vidyasri, I have one question. So, on which data set we will use the SRGM, and on which data set we will use the LLM SRGM models? So, have you identified the both data set?
So the goal here is using LLM to extract the data that you can apply the software reliability models on, right? LLM is simply becoming your data extraction and pre-processing module. So it essentially cleans up the data, creates a really well-informed data set from all these massive databases. Take GitHub, for example, Jira, for example, any other collaborative, platforms, just for instance. So LLM essentially extracts data from that and information from that and kind of gives you that recurrence and severity and subsystem level details in addition to that time to individual failures. So you could apply your software reliability models to that. So essentially LLM is a preface to your reliability model application. In other words, we're using LLM to extract the data for reliability models. So if we were to apply any reliability models with this amount of data, we're probably going to be applying like covariate models, combining, test effort and imperfect debugging sort of attributes embedded in them.
So any particular method you have you've done extraction for your LLM model?
This was a fairly just, kind of enhancing and improvising, fine-tuning some of the parameters as well as improving the prompt engineering using a basic GPT-4 turbo model. But with the amount of data that we have and some of the nuances that we had to learn, we did have to, this is the future work or this is the current work that we have been exploring. Just within the LLM, we had to create multiple layers and multiple models, as well as embed some of the machine learning components to it as a way of supporting the LLM models and to reduce the computational complexity. So that's the kind of nuances that we're working with or identifying. In terms of software reliability models, we're still sticking with the good old statistical models with covariates and all that beautiful approaches. That we are not changing much, but instead we are trying to use these LLMs so that we could extract good quality data. So we're making good predictions.
Okay, thank you, Dr. Vidya Sri.
Of course. Thank you.
Thank you so much, ma'am, for this insightful presentation. Now I request Professor P.K. Kapoor, sir, to felicitate our session chair, Dr. Deepak Kumar. So let's start with our next keynote address. Thank you so much, ma'am. Now let's begin with our next keynote address, where our session chair would be Professor T.V. Vijay Kumar, sir, and our speaker is Professor Rajesh Prasad Mishra, sir. Dr. T.V. Vijay Kumar, sir, is currently the Dean in the School of Engineering at Jawaharlal Nehru University, New Delhi, and the Professor in the School of Computer and System Sciences. He also serves as a concurrent professor at the Special Center for Disaster Research and Special Center for E-Learning at JNU. He completed his PhD in databases from JNU after earning his MPhil and MSc in Operational Research and BSc Honours in Mathematics from the University of Delhi. His research interests include database and distributed system, data warehousing and data mining, artificial intelligence and machine learning. machine learning optimization techniques, data science and big data analytics, and disaster management system. Professor Rajesh Prasad Mishra sir has over 25 years of research and teaching experience. He completed his BE and MGCGV uh, from MP and his ME and PhD from BITS Pilani, Rajasthan. His research interests include maintenance engineering, lean manufacturing optimization techniques, manufacturing system and RAM simulation and analysis. He has guided PhD scholars and is currently supervising in multidisciplinary areas and numerous projects, dissertation and thesis. He actively collaborates with international universities such as the University of Lisbon, LTU, Sweden, and UTK, a fellow member FIE of the Institution of Engineers in India and a senior member of the Indian Institution of Industrial Engineers. He is also associated with other esteemed organizations. Professor Mishra is an active reviewer for several reputed international journals and has published over 75 articles in peer-reviewed journals and conferences.
Uh, just want to correct one thing. Can you hear me?
Yes, sir.
Just want to correct one thing. At present, I am not the Dean of School of Engineering. At present, I am the chairperson of Special Center for E-Learning right now.
Oh, got
Just
it, sir. Sorry, my bad.
Okay. So I welcome Professor Mishra, and I think it would be a great pleasure to hear from him. Um, he's from the mechanical engineering field, I think, and
Sorry to interrupt you. Can you just make it to full screen?
what do you want? Hello.
Yes, sir. I just want you to make it to full screen so that we could just fully see the presentation.
Presentation, I think Professor Mishra would be giving. So I'm the chair of the session. So just wanted to say thank you to Professor Mishra for sparing his time to deliver a talk in this conference. And I wish we are going to learn something new, and definitely people will gain something out of it. Thank you, sir. Please start. Please, you can go ahead with your talks. Thank you.
Yeah, thank you very much, introducer. Am I audible to you?
Yes, sir, you're audible. You may start.
Yeah. Thank you very much for giving an introduction. And first of all, I'm really thanks to the Professor Kapoor and his team to giving me opportunity to talk over here in this conference. And since I am associated, I am really feeling bad. I'm not physically there. I always attending a conference of this kind and interacting and getting accumulated with their teams. But this time I'm really sorry, could not able to reach there. And actually I will be making my presentation short because I have a class since I'm not there. I'm there in the campus, so I have to take my class just so that I will cut short my presentation. But I will try my level best to put up the recent things, what is going on with respect to the integration of TQM, IoT, and sustainable manufacturing. Because these, one of my PhD student, Mr. Santosh Kumar Gautam, actually is working in a company and where he is doing this research and try. I'm giving a glimpse of slight his research and how we will carry forward. He still is doing this research on this particular area, and we trying to influence the company that how these integrations can be implemented, so it will become a good case for us and for the company as well. So once again, thanks, and then these are the contents of my presentation today. I will be going through the motivation, then we'll put a little perspective of a global development, and then how Indians are actually in this race, how they are doing. So I will be taking Indian scenario as a after independence. Then I will be showing little bit gap, what kind of a gap there and why we need to go. So there is a need for integration and what are the problems they are attending to. And then probably I will able to take you to the key takeaway of integrations and follows. So let us discuss about this that as we are facing, and it is not the today's scenario we are facing from the beginning itself, because none of the things we have invented, especially as an Indian contribution. Everything we are following the rest of the world how they are doing, and try to taking up into the our scenario and build. So it's happened to the all the sectors, but especially manufacturing sectors, that since we have not invented, so we are following and we will be followed for a longer period of time, because if somebody is inventing and putting first into the market, he will be the leader, or a seconder will be the leader, but the rest of the things people will be follower only. So because of this nature and these kinds of lackness somewhere in the process, we facing a lot of challenges in terms of industry. So there is a means, as we know that since I am in Pilani and I am delivering a keynote lecture in a Amity University, you can understand that how things are rapidly and globalizing, changing, and sending a representation all across the world. So that is how rapid globalization, and most you can just 1 or 2 months back you have seen that India is collaborating with the multinational and companies like they have come across the US, Europe, and Russia, and they are all across the globe. They are trying to show the presentation. So as we are showing our presentation, there are the challenges in the globe, means challenges to us as well, because there are other countries, they are doing much better in terms of all the perspective of the company, means manufacturing. So there is the rapid globalization. Another important challenge what we are facing is the dynamic in the demands and dynamic in the changes and changes in the customers expectations, because as we can see, we realize in the 90s that the kind of a product which we were getting, and if you compare slowly how quality has been increased of the product, and nowadays there is no compromisation of a quality. You can see whatever you are buying, it's have that level of a quality. So these are the development which has been more mature in terms of the time scale as going ahead. So that is how there is a also a demand from a company side that how to cater and means enable these things to be a much better way. And always turbulence, and it is dynamic. Never be either if you take the early days of the 60s and if you compare the 2020s and anywhere, it will always be a turbulence. Nothing will be stable there. So tackling this market, you have to be innovative, you have to be replicative, you have to be as much faster you can be transferring your ideas into the product much more be rapidly and quality ways you need to be tackle the market challenge. Then there was a pandemic, as we have seen, and it has been disastrous for the all across the world, and things has been changed, culture has been changed. Even there are some positive side like communication sectors, and this presentation has been increased, but yes, there are the challenges in terms of a cultural behavior, following the process, and things has been changed. So there are the effect is still our industry is facing. And another side, since we have presented ourselves in towards the global, so we are comparing our original product which is being produced in India in terms of the either it is what kind of a product things are there in the US or in Australia or anywhere. So it is now the product is no longer it is the specific to the particular city or a town. it is belongs to all across the world. So that is how these challenges actually we have, and we are tackling with the substantial kinds of tools which we are available, but still these remains challenges for a quite longer time, because as I have told, nothing has been invented from the our side we are following. So if look at the industry, this particular figure, as we started with the steam engine converted into the combustion engine, then there are sort of computerization take place, and then we have integrated the internet, and then mass customization and other cognitive technologies being added into the process. So similarly, we have to change our process accordingly. We have to, whatever the standard operating practices we have developed before these times, we have to modify, we have to taken care that how effectively and without compromising of the key performance indicators of a company has to be grow fastly. And the important thing is the learning in towards the companies. That is the another challenge which we are talking about. So if you looked up the global perspective in terms of global market, as I have shown you the figure, that if I can rate, because these the kind of a version were not available before COVID, we started understanding and segregating the development in a particular decade or a particular century. So if we started understanding the global perspective, so the Britain is the originator, and they started the steam engine, putting the manual thing into the machines. Then technology revolution changed during the First World War and Second World War. It has been a major impact on, especially for the application sides of the theory. I mean, science has been applied and being converted in the form of the various applications. So you can see here, first era was the Britain, second era Europe, American and Japanese. Third era started kind of taking the picture of a global presence. So digital revolution has happened. A lot of ITs and computer has taken their role of repetitive things and presenting, documenting in a better form of the processes. Then the now, which we are, just a verge of a next version of the industry categorization. So we are having the smart machines like DNC and CNC developed now. It has been integrated in terms of internet and other tools which can be a one man show of running a company kind of a thing is coming. So this is the how a global is moving. Now if you looked up the how we are here actually. So we actually started, if suppose very late in terms of the presentation in the world, but we are not behind much of the people of the world. So if suppose we start evaluating ourselves as a India, so we are a building phase started with the 50s to 60s, where we have focused on just to how cater the requirement and putting it. So building phase, that how things can be developed. Then there was a sort of a problem because of the war. So we means a little bit maintain the building things, but it not being accelerated. Then we started recovering after the in 90s, 80s and 90s, and taking to means industries also started showing their presence, because the agriculture sector was much more dominance in means the most of the financial issues, but now means in that era the industries is taking place. Our industry showing started presenting, and major things has come up because the regulatory and other things has been changed. So it is become more easier to means develop a company and opening a company. So a lot of things has been come up after the policies of 1991. So this is what the India. So you can, if you compare where people are inventing, we have never things as a invention kind of a thing. We started deploying and copying all those things. So if we looked up the gap and shown a kind of a development of the world is doing and India is doing, still we could able to follow a lot of Japanese tools and techniques like TQM is the most prevalent here, was most prevalent here, and almost now we 70 to 80% of a company could able to follow now in their own way of understanding the TQM. So the studies over the TQM improvement and IT enable smart factories and things are going on in that. But there are still, since technologies, as I have told you repeatedly, that not in our hand, it is coming from somewhere else. So real time implementation, yes, it is happening in a rapid way, that there is an acceleration that you can see in nearby also, that the kind of smartphones and the communication sector has been improved. It is the tremendous. It is I'm really we are appreciating. But since we applying those things and it is going into the real form, it still has a lot of challenges. So things has still need to be done to unify what we have learned from the Japanese tools and techniques like just-in-time manufacturing, TQM, TPM, and other policies. We are could able to stabilize, and then there is a further changes in understanding and translating these things with the new technologies is again come as a challenge. So there are a few more people able to do some work over. So few empirical validation model and limited cross industry validation has been done, but still need to be a much more study. That is how we started with understanding with our student and thinking that we can, if we see the changing of the perspective of the technologies and what we overcome with the implementation which is required for a company has a means barrier still. So we started discussing. So as we started understanding this taking into the TQM and then we integrating into the IoT and why we need those things. So as we able to cater the quality issues, but now we have to develop the smart systems and the data driven approach. So we also in building into their processes like a smart sensors which will be giving you the lot of data and critical data to overcome their failure. We also enhance our level to the breakdown, from breakdown to preventive to predictive maintenance. Yes, we started understanding and duplicating the companies and try to understand the real type of a problem. So we started engaging the digital team, and more importantly that now the steady state kind of estimation is slowly going up, and the real time monitoring things is more needed. So we started taking the measurement, immediately rectifying. So real time monitoring process is also rapidly taking place in terms of the thumb rail or heuristic approach, and then AI driven decision making where we can understanding much more factor than what we can evaluate. So this is how actually needed in terms of integration. Then there is the again problem with the process to change into that. So these are the some problem basically why still we knowing some of the things and we are very well comfortable with the older tools and practices, but they are not in a sync. There are problems in the synchronization or putting in form of a tandem lines. So if we able to do that, then definitely these fragmentation we can attach and make the process streamline. So looking at these perspectives, we try to understand the what I have discussed so far in terms of relating to the older tools and we can say older practices with the new developing technologies and what are the benefits we can have if we take to the level. So I have shown listed down into the some of the slide. So looking at these, there is another challenge is the scarcity of the resources, because you can see we are still facing that if you looked up, we are changing from the combustion engine to the electronic vehicles and so on. So if you looked up the electronic vehicle or EVs, where electric vehicles where you need some kinds of a battery, and for a battery you need to have a lot of the heavy metals which are not readily available. You have to look up that how you need to tackle these issues. So still there are challenges, and still we need to understand the dynamics of those process, how they can actually reflect on the product. Other than that, there is a huge demand of reducing the carbon footprint and the kinds of environment, climate changes issues, which is you can see now the climate, because of lot of things we have done in a rapid way, and we have not gone and understand the ecology of the world, and we are lot of facing a problems of the temperatures and other climatic conditions issues. So those things are also a big obstacle for all sort of a companies what we are. So we are looking how to reduce those utilization of good things, and we try to compromise or try to enhance our processes with looking at those actually constant. So the sustainable manufacturing is now will be taking every role with the help of the developing technology. So the waste reduction will be much more needed, and the demand of our. So if we can see how we will be profitable if we do the integration. So if we have understood very well to the TQM, and that is improving the quality, you can see. And if we can correct that improvement with the recent data science, that will be a much more rapid way we can enhance the product. And another thing, that how product can be survive, what is the implication after use of the product, if we can understand by the sustainability. So definitely all of the challenges cannot be tackled at a time, but slowly, and we will stabilize into the understanding of degradability or how to disposal of those products. And definitely, and it takes a few years to we can build up a sustainable world. So these are the challenges which I wanted to highlight with this particular talk, and try to think that if some other also can join hands with tackling these issues, definitely we will make the significant changes. So that is how we wanted to tackle, and my research student is taking care and is underway of studying these kinds of techniques. And because he is working in a company, so simultaneously his real time challenges is handling and try to incorporate into the research. So definitely we will able to come with the much more appropriate and realistic research towards the integration of total quality Internet of Things and the sustainable manufacturing. That's all. I'm sorry, I need to cut short because I need to go to my lecture class. So I'm just stopping here. And I'm sorry I could not complete much because there are a lot of things need to discuss and it will take a little more time. but I have another constraint. So
Sir,
really
sir,
apologize.
thank you very
for-
much. Sir, thank you very much for your talk. I think this is area very relevant when in the context of AI. Manufacturing area is a very, very important area of relevance. I just have one question, sir. I think I understand you have a class after this. Just small question. AI is going to have the biggest impact on manufacturing because that is where AI is going to have a serious impact on. So, what do you foresee about AI in terms of manufacturing, sir?
Sir, that is not the challenge or the impact. I am looking a very positive way that actually this will be reducing the two things. One is the repetitive work. Another is that hazard things where a normal human being may not able to operate, or it will be not good to operate. So that way it will be helping a lot, and the next future will be the disposing and degradation of the product, which will be converting to the sustainable environment. So these are the things we are looking, sir. If I'm sorry if I have missed up to.
No, thank you very much, sir. On the behalf of the conference, I would like to thank you for sparing time to deliver such a talk. It was very enriching, and hopefully, people who have gone through the talk must have got a brief idea to work on in this area. Thank you very much, sir. Thank you.
Most much appreciated.
Thank you. Over to the coordinator, or person who's coordinating the session.
Hello, sir.
Yes.
Can you hear me?
Yes.
Thank you, sir. Thank you for the insightful presentation. I have a small question. From the implementation point of view, what company should prioritize first if they wish to adopt this integrated approach?
Prioritizing is that means now things has been changing rapidly, and as we have understood the sustainable goals, so we need to see the kind of sustainable goals, and then we will focus on the particular processes and adopting the technology. I'm sorry if, because I want to put a very general perspective, not the company specific. So basic thing is that we need to handle and make the word sustainable, and that way actually has to be prioritized, and definitely there will be a lot of regulations will be coming means in next few years, that we will be bound to actually prioritize all the kinds of a product or a process which should not harm the system.
Thank you, sir. Thank you.
Okay, sir. Thank you very much, sir, for this session. I hand it over to the who's coordinating the session, the coordinator of the session.
On behalf of organizing committee from Kapoor side office, we thanks to Professor T. Vijay Kumar to session a chair. And thank you, Ms. Asha, for your nice presentation, and we get insightful actually details in your presentation. Thank you very much, sir.
Welcome.
Thank you so much, sir, for the presentation. That brings us to the end of this session, and we'll resume at 12 after the high tea break.
Thank you. Thank you very much.
So, good afternoon, all. Let's move on to our next keynote address session. And the session chair is Professor H.D. Arora. Professor H.D. Arora is a professor and head of the Department of Mathematics at Amity University of Applied Sciences, Amity University, bringing over 25 years of academic experience in teaching, research, and academic leadership. He holds a PhD in applied mathematics and has established himself as an experienced educator and researcher in areas such as fuzzy sets and systems, optimization, reliability analysis, and applied mathematics. Professor Arora has strong record of scholarly contributions with more than 80 research publications in peer-reviewed national and international journals and conference proceedings. He has also authored and contributed to 12 well regarded textbooks and reference books in the field of engineering, mathematics, and statistics, which are widely used in academic programs across universities and technical institutions. His book publications cover core and applied topics such as an engineer mathematics, applied mathematics, numerical methods and optimization, probability and statistics, differential equation, and related quantitative subjects. Professor Arora's blend of academic excellence, research productivity, textbook authorship, and doctoral guidance underscores the significant contribution to mathematics, education, research culture, and student development. So, the speaker of this session is Professor Subhashis Chatterjee. Dr. Subhashis Chatterjee obtained his BSc Mathematics from the University of Woodburn in India. He obtained MSc Mathematics and PhD from IIT Kharagpur, India. His area of research is software dependability analysis, reliability, and bioinformatics. Presently, Dr. Chatterjee is working as a professor in the Department of Mathematics and Computing, IIT ISM, Dhanbad, India. Professor Subhashis Chatterjee is a senior member of IEEE. Dr. Chatterjee has completed various extremely funded projects on software reliability and statistics. He has 26 years of teaching and research experience. He has more than 60 international and national publications. He is the reviewer of various international journals. 12 students have completed their PhD under the guidance of Professor Subhash Chatterjee. Recently and presently, he is guiding 5 research scholars in various areas of theoretical computer science. Now, I would request Dr. Chatterjee to may start his presentation.
Am I audible?
Yes, sir.
Okay. So, good morning to all of you, the organizing committee and the honorable chair who is there, Professor Aurora, and other guests.
Sir, actually, your full face is not visible. Please lower down your camera, sir. Your face is not visible.
My face is not visible. Okay. Is it okay now?
It's okay. It's okay. It's okay, sir.
Okay. So, and the other persons who are present in the audience, the distinguished guest, and so I'm already, they have given my introduction. So I'm as a faculty at IIT ISM Dhanbad in the Department of Mathematics and Computing. So my area of research initially I started with software reliability, and then I started with the software dependability analysis, and then now also I am working a little bit in the bioinformatics area. So with this, let me start. Let me share my screen with you.
Sure, sir.
Is my screen visible?
Yes, sir.
Okay. So now just maybe for that internet, if there is no problem, so I am just, can I switch off my camera and start it? Okay.
Yes, sir, you may
so if it is feasible, let me start with that. Today's my topic is your software dependability analysis, mathematical modeling, and historical evolution on experimental evolution. So basically, software dependability analysis. You see that the name of the topic. There are many other things are written: mathematical modeling, historical evolution, and experimental evolution. Usually dependability analysis earlier it was not there. Initially it was the reliability. When it started with from the hardware reliability, the concept came in the software reliability, and it was just only reliability. There are different type of models. They have parametric models, then later on non-parametric models has been developed. So like that evolution has taken place, and at the end means now in 2000, maybe in 2010, 2015 onward, people are more interested on the early phase and the dependability analysis of the software, which is more wider aspect than reliability. Reliability is only about the reliability, but dependability, it consists of reliability, performability, availability, risk, then security, aging. So many things are covered in this dependability analysis. So, so the outline of the talk is introduction and mathematical foundations, dependability attributes, historical evolution of reliability models, input domain and fault reduction models, modern developments in dependability, early phase reliability. So these are the different fuzzy deep learning methods, and some in the last part you will see some of my work, our work, I will say our work of our my scholars, or we will discuss how we can. How we have used that fuzzy logic and deep learning techniques for dependability analysis. So that will be the last 2-3 parts. That is a major highlight of this your talk. So here initially I will discuss about some that software models, how it has evolved. Maybe a little bit of mathematics will be there, analysis, and then finally I will go to your this deep learning part. So software dependability, what is that? What is that software dependability? Is the justified confidence that a system delivered correct, secure and timely services under stated conditions for a specified period of time. So that is that your software dependability. It is a little bit different than your reliability. Reliability is only about that the faults and the estimation of the faults, the number of faults, remaining faults. Then there are many other things we consider, that your perfect debugging, imperfect debugging, and then your release, then conditional reliability. So those things, it is only about the reliability part. But when I will talk about the dependability, is more broader aspect. It is more broader aspect. So it is basically that a system delivers correct, secure, and timely service. So these three terms are very important in case of reliability. It should be correct. That means reliability is there, secure, and its timely services must be there. Availability and performability must be there. Okay, stated conditions for a specified period of time. Now, what are the things in the reliability integrates? These are the following things that integrates the reliability, dependability, that is your reliability, availability, maintainability, performance, aging, resistance. This is another one, and security. Say, generally, if we consider only reliability, availability or maintainability, that is not, or even the performance, that is not, it will not cover the entire thing. Aging is another one problem nowadays, and people are working. Many people are working in that, but aging is a really big problem in case of your software. Okay, because as time passes, that due to aging, there are different type of faults incorporated. It comes in the operational phase, so different type of faults are also incorporated, which are these faults are different than the faults we generally see at the time of testing. Okay, and that is sometimes if you see, then when you use this Android phone or that mobile phone, if you see after a few years of time, maybe 3 years or 4 years, your phone gets slow because of that aging problem of the software. Okay, it is getting slow, or sometimes it gets hang, sometimes frequently it hang up. So there are many other things crop up because of that aging. So that is also your comes under the dependability analysis, because how you can rectify those situations also. How can you handle those situations? That comes under that. Then the security, we all know the security of the software. There can be different outside attack, or the people may use that fraud things can happen. So those things comes under the security part. So dependability extends reliability by incorporating operational readiness, safety, and protection mechanism. So now first is the reliability. Initially what I told you, initially it starts with the reliability analysis. Okay, so reliability analysis, when it started, at that time it was, a dependability concept was not much studied. It was only the reliability people started in the late 70s, or maybe from 70s, and then till 90 or late 90, it has started about, most of the works are on the software reliability, and different type of models has been developed in the area of software reliability. Okay, so reliability definition, it's almost known to many people. So just let me, as an introduction, let me tell you that if I say T is the random variable which denotes your time, then your or says a lifetime, you can say, then that reliability we define is that RT is equal to your probability of T greater than T. That means it is beyond a certain time also it is working, it is functioning. That is the way how we define the reliability part in this case. Then the failure intensity, in the reliability, failure intensity also one part. With the failure intensity we can estimate the reliability with this formula, that is your e to the power minus 0 to t, that is your lambda t dt or lambda u du, like that we define. So that is the probability of successful operation of a software in terms of software, if I say, under a specified time and a specified environment. Okay. Then the different type of models has been developed in this area of your software reliability. The one very famous model in this one, but that time it was only the reliability part. I am talking about that particular era. That time your Goel has developed the very important model, that is your NHPP. That is NHPP, that means your non-homogeneous Poisson process. Okay, this is the first foundation, you can say, in that your particular area. The fault count, if I say the fault count category models are also divided into different categories. So fault count is one category where the number of faults arrival, the number of faults arrival at different time intervals, that follows a particular distribution, and that distribution is your non-homogeneous Poisson process. That Poisson distribution, but why it is a non-homogeneous? Because its mean is that is a time. Okay, function of time. Mean is a function of time. That's why it is called a non-homogeneous Poisson process. So mean value function he has obtained using that concept is this. There are a lot of assumptions also there. So this is the first model he has given, and based on that model, the conditional reliability is estimated by Goel is this one. It is the expression. It is e to the power minus mt plus tau minus mt. So that tau, that mt expression, if we put it here, then this becomes the reliability, conditional reliability. So your so here, if you see that the expression of the reliability, what he has interpreted, that with that mission duration, that RT decreases, as testing progresses, reliability increases, and you're directly linked with failure intensity reduction. Okay. So now that reliability, and now in this, when I talk about that reliability, this is the first model came up in the reliability. Now, other than reliability, there are many other models which are, there are many other parameters which are considered for your dependability. The reliability is one, then availability is another one aspect which is very much required for dependability. Then availability is measured by the mean time between failure divided by MTBF plus MTTR. This MTBF and MTTR is your mean time between failure and the mean time to repair. Then your maintainability is another one thing. That maintainability, that means your performance is a response time, throughput, and the resource utilization. This is also another one aspect for dependability. Maintainability and performance, basically maintainability and performance. They both the things comes under your dependability, but performance metrics is much more important than the maintainability part. Then aging and security. Aging means here memory leak. What are the terms? What are the things happens due to the aging of software aging? That is your memory leak, resource exhaustion, and fragmentation. And there some work is there with the viable hazard rate. They have used and they have developed this your software aging. They have tried to tackle the software aging problem there. Now this is your now let us come to this. What is the problem? Your deep analysis, if I do this about from the reliability to your dependability part, that is system characterization. There is system, this your established reliability modeling scope and dependability target. So here is the safety critical system, mission critical system, and large scale distributed system where this dependability analysis is very useful. Dependability attributes, what are there? Are actually dependability in the early phase. If we are going to do, there is no data in that. So there are certain attributes which contributes to dependability. That what I have told you. So dependability we can express as a function of all these attributes. Okay. Reliability you have defined. Hazard rate is like this. Now this dependability when we are going to do in the early phase, that is what is our main work. That is the early phase. Your reliability or the dependability analysis. There is no failure data. Most of the reliability models, if you see, these are test data. There you get the data and after the testing phase over. But in the early phase, there is no your such data are available. Only we have some your metric. With those metrics, we try and then we take the your expert judgment, and based on that we use a fuzzy rule base and deep learning genetic algorithm, and then we try to develop these different models which we can predict that number of faults. But in case of your early phase, number of fault prediction is not that much important, but the most important part is the identification of your fault prone module and ranking those modules, such that you can take the measures when you are going to develop the software. You can take the appropriate measures based on your that ranking. So now let me come to that. Now this reliability, what I was talking about, that initially it was a concept came from the hardware reliability. So initially everything based on the your hazard hardware inspired data. If I divide that part, that time initially the model started with the concept of your hardware reliability. That is hardware reliability mostly hazard rate based models. So here if you see that hazard based models initially developed, first model was almost, you can say this is the first model. Zelensky-Moranda model came up in 1972, where it is a hazard function, and based on that the hazard rate expected time has been developed. Okay, and these are the different assumptions for that fixed initial fault content. Initially they have assumed that number of faults are your constant, that is your n, and then failure occurs independently. Failure rate is proportional to the remaining fault, that is this part, and then perfect debugging. That is the thing. This is the first model, you can say. That is the concept came up based on your hardware concept. From there they have came, and then that it is modified and it was given as your where this is that your n is the initial number, phi is the proportionality constant, I is the failure count. Okay. Now next it was modified by C. Culberton. Yeah, he has considered that your failure rate is your not as a constant, is a function of time. It is a linear function of time is considered, and based on that they have calculated. The thing is, these two models I have just given. There are many other models in this particular area, but these are all initial. In the 70s and early 80s, there are a lot of such works has been done based on this hazard rate part. Then the NHPP came up. That is the Goel-Okamoto model, which is a totally a different type of concept they have considered. That is a non-homogeneous Poisson process, and they develop different models. And this is that Goel accommodation model. Actually, this is how it has developed. That MT, it is function of time, then lambda t, then conditional reliability has been estimated using the Goel accommodation model. Now this is there is another one very important model is your SF model. That is Yamada SF model. It is this one. Now let me just quickly go through this and let me come to the actual part. That is the dependability part. So this is your what are the key assumptions we make in the your NHPP type of model. Then this is Yamada's growth curve, how this reliability growth increases. And this is another one area that time in early 80s came up, that is your input domain based model. This is a very important model because it covers a very important area, that is the input domain, because software failure occurs because of the input profile. Okay, that so that input domain based model, that very few work has been developed. So that input domain based model, Ramamurthy Bastani is the first person who has given idea about input domain based model. So these models are like that. It is input domain based model. It is considered the core idea is software reliability depends on how users actually use the system. This is the most important part in software. That is input profiles. How we use depends on the user. Reliability, most of the cases in case of software, not in the hardware, it depends on the users. Okay, and users, what type of operational profile they are using and input profile they are using. Based on that, reliability depends on that mostly in case of software. So the input domain is partitioned into different part, and based on that, the reliability is calculated with the probability is assigned. That probability occurrence operational profile occurrence. Based on that, the reliability formula was given like this. And then from there, they have derived this your lambda t, that is hazard rate. And once you get the hazard rate, you can calculate the reliability, and the reliability expression from using that, it becomes the reliability expression is this one. This is the input domain based model. This is a very important area of research in software reliability, but very few work are available in this particular area. So this is the way initially the software reliability started. That time dependability was not there. And then the concept of dependability, early phase dependability, reliability, all those things came up here. So now let me just quickly just show you these results. Okay, now let me come to, this is that your how the reliability they have calculated in the input domain based model. I think I have now 8 minutes time. Okay. Let me just quickly come to this your early phase. This is the your main topic which I want to discuss. That early phase, people are more interested than testing phase than the early phase. Early phase means when you are going to develop a software. Before that, how can you estimate your reliability? How can you say something about the reliability, or how can you identify that what are the different modules will be fault prone, or how can you estimate the faults? Okay, so this is the early phase. This is the early phase. The main motto behind the early phase reliability predictions. Okay, so then initially there are if you see, there are work by Fenton and there is work by Minzy. What they have done with some data, they have tried to find out the number of faults or identifying the fault prone module. That is the reliability aspect. That means, and now to do that your early phase analysis, there is no failure data. What I was talking about, there is no failure data, only the metric they are taking, and based on the metric they are calculating that part. Okay. So in the early phase, if you see that input artifacts are your requirement complexity metric. This is a metric, design your coupling metric and code metric. There is a LOC or cyclometric complex. So these are the different metrics which are used for your early phase reliability analysis or the dependability analysis also. So if I say then as a function, if I express this your reliability, then it is your f of function of x1, x2 up to xn, where xi is the software metric. What are the different metric you are using? So as a function of that, and then your f hat is your fault predictor. Okay, so prediction approach is your either statistical regressions we have used or fuzzy inference system we have used there. Okay, but in our case we have mostly used a fuzzy inference system. So that, but if you go for your linear prediction model, then with this is the requirement based metric. What are the major factor which plays a very important role? That is your requirement ambiguity index, requirement volatility, and functional complexity. Based on that, you can have a linear model like this. For early phase software reliability estimation. Then your if there is your higher ambiguity and volatility increases, then predicted fault density will be your increases predicted fault density. So fault density will increase if these two are very high. Okay, so this is the main concept, and based on that it was developed. This is a linear model was developed. Now, what are the different type of your metric? Let me just discuss about the different metric which we use in the early phase. One is your lines of code. The code metrics, that is the lines of code. Lines of code means this is a very important, it plays a very important role. The lines of code means how many lines of code you are delivers at the end. That is a total the software lines of code. This is the one metric. That is called the LOC metric. In the 1000 LOC is your 1 kilo line. So this is one metric. That with that we try to, with the expert judgment, that if your lines of code are very high, there is a chance that the complexity will increases, or your fault proneness also increases there. So like that interpretation comes up. Then there is another one metric, that is a psychometric complexity metric, that CC is signifying a significant software measures that aids in evolution of program dependability during the design phase of a software development, and due to increase in CC, software become unreliable, unavailable, and insecure. This is another one, that is your design complexity. This is basically design phase. Previous was the requirement phase. This is the design phase. So one is your design complexity. That is the software design, means the architecture as well as the your algorithm. That is the detailed design part. Okay. So software module structure is measured by design complexity, and design complexity module, a complicated structure of a software module has a higher design complexity. Obvious. If your structure is very complex structure, design complexity increases there. Automatically, if the design complexity increases, there is a chance that the fault proneness increases. Okay, so that is the basis for your interpretations are made like this. So in that case, we have also some work in that software performance, security, and availability of software system. And then the branch count. This is also another one for the design. That means on your model, you are making your modules. So they have a calling relation. So there is a branches are there. So that branch count is also one metric. So another key software metric in the design phase that influences the software dependability and the branch count. If the number of branches increases, that means in the control flow graph, it increases automatically. That means one module is calling 3-4 modules, so automatically complexity increases. So there is a chance that there will be some sharing of this logic or the control statement. So automatically your fault proneness increases there. So based on these metrics, we try to develop a fuzzy rule base for your early reliability or dependability prediction. What is the requirement metrics are often imprecise. So because of that, fuzzy rule base we have used, because initially there is no data. These are all some metric, and the metric values we take from the expert opinion. So fuzziness is more here. So because of that, that's one example is like this. If complexity is very high, volatility is very high, then fault risk is very high. This is the way how we interpret that. But then fuzzy inference system has been developed using that your if I say the risk is one component for your dependability part, then membership of that is computed with this one, and then after fuzziness we can defuzify using this method. So this is one your membership degree. This is the metric values and your low, medium, high. So this is a triangular your fuzzy membership has been used in this case. So now, if I pictorially, if I say the fuzzy inference system, it is this is your requirement complexity, requirement volatility, code complexity. All these things comes to the fuzzification. Once with this we do the fuzzification, then we generate the fuzzy rule base. The fuzzy rule base, then we go for inference engine is there. Along with these two, we make that inference makes that output will be a fuzzy output. Then the defuzzification, and then the predicted reliability. So this is the way how this your fuzzy inference system work in early phase. So now there in the early phase, not only the fuzzy, then we have used your neural network also to identify the fault prone modules. Okay, so the neural network model is also like this. And the early reliability prediction is a requirement and design matrix. This is another one, that input metric, then fuzzy inference system. Then we have used the deep learning from the rule base. The deep learning has been used to estimate the reliability. Okay. And these are the different your metrics. So requirement complexity, your requirement volatility, design coupling, and your code complexity. So this is your membership function used there, and defuzzification, fuzzy output is defuzzified using this formula. Then deep learning, as usual, deep learning, this is a hidden layer 1 and hidden layer 2, how it has worked, that weighted part, and this the reliability computed using this one. Sigma is a sigmoid, your activation function is used, and this is a loss function which has been minimized. Now, based on this, just let me come to, this is your the reliability estimation part, which you have to minimize this one. Do I have time, or it is already over? Excuse me, do I have time?
Yes, sir. Just five. You can, 5 more minutes we have for the session.
Okay, just 5 minutes. Okay, fine. Just I will show you those results, how the flowchart. So this is one which is dependability analysis, that architecture part. We have used a neutrophobic your inference system. This is the architecture, how this neutrophobic system works. So this is your neutrophobic inference system where the truth component are there. Then information comes and expert knowledge, that is the expert judgment comes here. And this part is the neural network I have used. From here, the dependability attributes are coming. This neutrophobic part is considered for generating of the dependability attributes, and that is when feed to the neural network. Okay, and that Elman neural network, and there we have used the Molodim's distance, and then it is you're doing the classification, software classification. That is the way how it works. This is another one flowchart of that. So how this program works, that flowchart has been given here. And the proposed, this is your, what I told, a meta heuristic, that is your genetic algorithm, and Elman neural network has been used, so that the algorithm is like this. We your select a random initial population, fix a dimension, then decode chromosomes and develop a network like that. So this is that your flowchart of GA and your eRNN. That flowchart is this one. Now let me just show you the ranking. What we do with the ranking, there is a fault proneness that is due to reliability, security, maintainability, risk, and aging. That fault proneness are considered. That if it is which are very highly fault prone, then the next like that we do. And if it is a very highly fault prone, that is a non-dependable software model. So less fault prone, that is dependable. So these are which are not your highly your fault prone or non-dependable. So you have to take the appropriate measure to make it the dependable. And where is the lacking? So you have to take care of those parts. That is the main motto of this type of work. So this is one your data set. You can say this is your Fenton data set and other data set you have used. This data set. These are all some flight control software and storage management software data set, with which this is the rule base. This is the actual rule base what I was talking about. That if LOC is very high, then psychometric complexity is very high, design complexity very high. And then what will happen? That is, aging will be there, maintainability, performance, like that, the rule basis. And then, if you now, the question is how we have done this one. This is from the expert judgment. We have given them the questionnaire, they have given us, and based on that, we have generated this rule base. So these are the different rule bases is constructed. And actually, finally, if you see that requirement, how we do that prediction architecture, requirement matrix, then code matrix, then prediction model, and predicted fault your risk. So these are my references. Thank you.
Thank you, Professor Chatterjee, for your valuable and insightful presentation. So now we can ask a question from the audience.
You showed us this dependability matrix.
Right.
Yeah, in there you have given aging resistance.
Yes.
What is the concept of aging resistance? Because we feel it is the hardware which ages, and software is something. It might be old or
yes. Aging in case of software, though I have not incorporated till now in the dependability analysis, but aging I am one of my scholars is doing the rejuvenation part. So software rejuvenation means aging occurs due to say maintenance. Highly means say continuously you are doing some maintenance work for the software is running for say 10 years, 15 years, and it has become old. And you are introducing, changing the codes, and the functionalities also changes. So automatically what happens, it is due to aging, there are different type of faults are also incorporated. So because of that, software gets slowed down, some performance also degrades. That is called the software aging. And then how can we improve that part? That is the rejuvenation part. How can you improve that part? And there are different type of faults. Those faults are not same as this type of faults which occur in case of software. So software aging is that, then the performance degradation work. So the performance degradation is there, so that means it is not a dependable. So how can we improve that part? That comes under software rejuvenation. So that is the concept of software aging here we have considered.
So you are saying if any maintenance has gone in the module and you saw some performance degradation, how you know that it is not because of some degradation in performance of the hardware? It's not the software, or some combination of input that is coming, which is a once upon a blue moon type phenomena, and
Yes.
the performance is not coming up to the mark. So
Yes,
these
that can happen. It is aging. Say that is there. That is there. That is, it can be the problem. Say if the software is not functioning properly, if the software is specifically, if the software is degrading in the performance or the software getting slow, then it is related to the software. If it is the hardware, then you can see that is because of the hardware problem this is happening. But this aging, what happens there, it can be also the mix of these two. So that can be also considered. That I have not studied in those areas. But in the aging, only due to the software, but the software is getting, performance is getting degraded. If you see the software engineering concept, if you see that one, the aging occurs after a certain period of time due to the heavy maintenance, due to upgradation, due to some your changes in modularity, your functionality, new functions are introduced. So a new course has been changed. So for after a certain period of time, software performance getting delayed, slow down, getting delayed. So that is specifically because of the software, not for the hardware. And those situations are called as software aging related issues. But it can be, hardware also can influence, that is also there, but we have not studied in that direction.
Sir, I have one question for you.
Yeah, sure.
In one of your slides, you have mentioned early phase reliability procedure prediction. In your opinion, at what stage of the software development life cycle dependability analysis deliver the maximum practical benefit?
Actually, early phase means before going to start even the requirement, your analysis. If you see the software engineering part, the software development, when they start, there are different phases of life cycle, used to say, for software development. So one is the requirement analysis, then is the design, then is the coding, then the testing, and like that it goes. So software development before going to, and whatever the reliability models we have developed, or till now the people have developed, these are based on the testing phase data. That means after the completion of the entire development, when it goes for the testing, wherever the failure occurs between the different times, so that has been taken, and then we have developed the models. But people are now that if you go to the industries, and most of the cases people are interested that at the beginning of the development process, how can I at least get some idea that what will be the reliability of the software, or which what are the factors which will affect the reliability of the software or the security of the software, that means on the performance of the software. So that is at the beginning, the starting. So there we don't have much data. So what we are doing, if you see that there are certain works are also there, based on that we have started. So we collect those metric. The metric is already there. So suppose the requirement phase, there are 4-5 metrics are there. Design phase, there are different metrics are there. And those metric values, if it is some are very high, some are very low, like that in the scale we have mentioned, and that we give the questionnaire to the experts. So experts give their suggestion. If these are the things happen, then the software will be very fault prone, highly fault prone, or moderate fault prone, like that it comes. And based on that, we generate the rule base first. Because metric values you have to generate, the rule base you have to generate, and that using the rule base, you generate the metric values, and then from there, you can use your machine learning or deep learning techniques such that you can estimate that rank the models. So this is at the beginning, at the initial part of development, such that they can get an idea that what are the models will be more fault prone, and they have to pump more resources for your design. They have to take care in the requirement phase or the design phase or in the testing. They have to pump more resource there such that they can identify those faults. So this is a measure they can do at the beginning itself.
Thank you once again, Professor Chatterjee. Thank you very much.
Thank you so much, Professor Subhash Chatterjee, for this wonderful and insightful presentation. Now let's end the session. I would like to request Professor P.K. Kapoor sir, Professor Prabhakar sir, and Dr. Anil Bhutani sir to felicitate our session chair, Professor H.D. Arora.
Vasi sir,
Yeah,
Professor Kapoor wants to talk to you.
yeah, sure.
Thanks for accepting our invitation.
Thank you, sir. Thank you. Thank you.
I had a question. I came late.
सर आप रिक्वेस्ट किए तो थोड़ा सा आना ही पड़ेगा. Thank you.
Yeah. So I was also wondering whether we can have a model where you can determine, hardware aging and software aging both together.
Sir, yes. I'll try that.
Yeah, something like, this aging started, Doi and all, they started working. And now,
Right.
I think you are the first I see after a long time to talk of software aging, and people stopped talking. I also started doing it much earlier, but
Yes. You have many people. I have seen that, sir.
But anyway, this is good. Nice to see you. Please
Okay, thank you, sir. Thank you.
keep in touch. Anytime you wish to come, we can pay for the travel, and don't please find a suitable time. If you started,
Yeah, sure, sir. Sure.
Have you started with
Future, if I get time, sure, I will visit there.
Yeah, something in machine learning? Have you, has your group done anything?
Yeah, we are using machine learning also in the different areas. We are using that.
Yeah, deep learning, please.
Deep learning and machine learning we are using, right?
So that I can call a couple of
Okay,
people.
sure, sir. Sure.
Thank you very much. Thank
Okay, welcome, sir. Thank you.
you.
So can I?
So let's start with our next keynote address. Our session chair is Professor Dheeraj Pawar sir, and the speaker is Dr. Neeraj Kumar Goyal sir. So Dr. Dheeraj Pawar sir is working as a professor of statistics and head research and consultancy at Amity Institute of Applied Sciences, Amity University, Noida. He joined Amity University in 2006 and has more than 23 years of teaching and research experience. He completed his MSc Mathematical Statistics and MPhil Statistics and a PhD Statistics from Maharshi Dayanand University, Rohtak. 6 PhD scholars successfully completed their thesis under the guidance, and more than 40 candidates completed their PG dissertation under his guidance. He published many research papers in various reputed international journals and presented numerous research papers in various national and international conferences in India and abroad. He worked as resource person in many workshops and an editorial board member or reviewer of many reputed journals. Dr. Neeraj Kumar Goyal sir received PhD degree in the year 2006 from IIT Kharagpur in reliability engineering. He received the Bachelor of Engineering Honours degree in Electric and Communication Engineering from MREC, Jaipur, Rajasthan, India in 2000. He has served as an executive in MS Secure Meters Limited, Udaipur from July 2000 to July 2001. He is serving IIT Kharagpur as faculty member since 2006 and is currently serving as professor and chairperson of Subir Chaudhary School of Quality and Reliability. He is also the vice chairperson of the Career Development Center at IIT Kharagpur. He is also the associate dean strategy and analytics, IIT Kharagpur. He has guided approximately 60 MTech and 2 MS and 9 PhD students. He has co-authored the 3 books published by Wiley and Spring. Now I would like to request Dr. Neeraj Kumar Goyal to start with his presentation.
Okay, Dr. Neeraj Kumar Goyal is going to present his talk on the network reliability. Welcome, Dr. Neeraj Kumar Goyal. Please go ahead.
A very good afternoon to all. Hope I'm audible.
Good afternoon, sir. Yes, you're audible.
Okay. So, respected chair, session chair, and dignitaries, as well as
Sir,
all the
sorry to
participants.
interrupt. Can you just share your screen? Like, can you share your presentation in full screen?
Yeah, I'll do that.
Thank you so much, sir. You may start.
So, I think I've been sufficiently introduced. This is some few slides about me. So, it's already been done. I've included some list of the papers which is related with my today's talk. They may be referred. I've also shared this presentation. I think if those who are online want to refer, can refer it from the chat. These are some projects which I have done, research projects and consultancy projects. So today I'm going to talk about network reliability in general and with focus on multi-state flow networks. In general, like if we see any network, we can represent the network through graphs, but any network, whether we talk about let's say electrical networks, communication networks, road networks, all these networks are designed so that there is certain commodities like the data, electricity, vehicle, goods, etc. They need to be transferred from one place to another place, or one piece of hardware to another piece of hardware. So here, this form a network. So network in a way gives us an opportunity that with the network we are able to enhance the reliability. Like there can be end-to-end connections, but there can be connections which are there through other nodes. So these things helps us to these things will help us to see that we are able to meet higher reliability criteria because of the networks. So but these networks in general, let me just briefly discuss. Let's say if there's any two nodes, so we can connect directly and flow the commodity. We can have networks which can transfer through other nodes. So there are various criteria used in the network reliability domain. So first is like connectivity based, which is kind of research which has been carried out around somewhere around 1980s to 2000. So here we try to formulate the reliability or try to find out the reliability considering that two nodes, let's say this is my starting node and this is my end node. We call it like a source node and the terminal node. These nodes are connected. So these can be connected either through this link or through this path. So whenever there is one or more than one path is available, you will be able to have a reliable connectivity. So in general, if we go with this, then we will have various ways of representation of reliability. Many times we represent the reliability as a terminal reliability, which is between the two terminals. That means source to terminal. Many times we want to have a broadcast reliability. That means when we are transferring the data from here, it is reaching to all other nodes. So that is our broadcast reliability. Many times we are interested in, let's say, any network which is having some critical nodes. So we are interested in reliability of those critical nodes being connected together. So that we call it as a K-terminal reliability. Then superset of all this, like where all nodes are connected with each other, that we are calling as a all-terminal reliability. This based on connectivity has been done. However, practically having the success criteria only based on connectivity is not enough. So later on, then people added the criteria which was capacity criteria. So here each link or node was considered to be in two states. Either it is working, that means whatever is the design capacity it is meeting, or it is failed. Failed means zero capacity. Okay. Now because of this, so again this remained a binary problem, but here capacities were taken into account. So it may happen that since source to terminal is connected with this, but let us say if I want to have 100 units of data to be sent from source to terminal, but this link capacity is only 50. So capacity is 50 per second, but my requirement is 100 per second. So that may not meet the criteria. So in that case, 50 may be sent here and 50 may be sent here. So 50 here, 50 here. If we send, then my criteria will be met. But in this case, if any of the link fails, let us say if this goes off, then my reliability criteria will not be met. So here, a single path may not be sufficient to carry the capacity requirement or meet the capacity requirement. So for that, we have to have multiple paths to be joined together, and they all should be successful. And so those combinations of path are found, and that helps us to evaluate the another reliability criteria which we call it as a capacity related reliability. We also developed this formulation was mostly implemented for 2 terminals, but we did one paper, and there we also did it for the multiple. So it is almost similar to K terminal reliability. Here what we did, we suggested that if different source and terminal, like from one source to different terminals, if we have the different flow requirements, so what is the probability that it will meet the flow requirements? So that we call it as a multiple node pair capacity related reliability. But nowadays, as we see that these flow networks which we are having, these flow networks may not be having only 2 capacities, that means 0 or full. They may have in between capacities also. These many modern flow network, they have it, and this is happening because of partial failure, or if there is a maintenance going on. Let us say on the road, if we see that if let's say one vehicle is failed, so it may jam one lane out of the 6 lane, but other lanes will be available. So that way what will happen, it will have the partial capacities available. Weather conditions, so for communication type of networks, weather also plays another role, and because of which the capacity may be deteriorated. So because of that, the more practical evaluation of network reliability is now coming up as a where the network components like links and the nodes are having the multiple capacities with their associated probabilities. So this is the this topic of discussion today. I'll briefly introduce you to this. Though I have a good number of research papers here, which you can refer for the details. So for flow networks, like every component, whether it is node or a link, it is having we are here giving as an integer valued random variable. So capacity is considered to be integer valued random variable, like 0, 1, 2, 3. 0 means it is completely failed. 1 means the capacity level is 1, capacity level 2, 3, like that. So this form a discrete distribution of the links and the nodes of the capacities. Now this distribution, we use it for the reliability determination of the network. General criteria whenever we use for reliability, because it is very difficult to model dependent networks in these evaluations, but if there is a dependency, we can modify these algorithms to consider the dependency. But for this method, we have considered that these distributions of nodes and links are statistically independent of each other. The flow in the network should satisfy the flow conservation law, and the graph is connected without any self loops. Generally, whenever we discuss reliability problems for connectivity, whenever connectivity is the criteria, we start with 2 concepts. Path sets, as I discussed, path sets, the minimal components which together will lead to the successful connectivity between the 2 nodes, or as per the criteria for all terminal, then all nodes, etc. But cut sets also forms a very good basis for reliability evaluation. Cut sets gives us, like if we go with the previous example here, like here, if cut set will divide the network into exactly 2 parts. Like if we see, so if I say this is the element 1, this is element 2, this is element 3, then if element one itself fail, it will not be cut set, because still the communication can happen. So cut set effectively divides the network in two connected networks. So like link number 1 and 2, if they fails, then the network will be divided in two connected networks. Source will be only sole isolated, and this node, terminal node, will be only connected with, let us say, node 1 with link number 3, but there is no connection between source and terminal. So these minimal cut sets, so if any of the minimal cut set is true, that means network is unreliable. And similarly, if any of the path set is true, that means network is reliable, that means network is working. So using these two concepts, most of the theories have been developed in reliability evaluation of the networks. Sorry. In case anybody feels like having some suggestions in between, you may provide. It's not a problem for me. Okay. So these minimal cut sets and paths, like when we go for capacity related reliability, then we combine the path sets into combined path sets. And in cut sets, we take a subset cut, because it is not necessary all the elements of the cut sets fail. Let us say here, if only link 1 fails, then my 100 capacity criteria will not be filled. So subset of minimal cut 1 and 2 will also be a cut set here. So that's why we use this subset cuts for the when we calculate the capacity related reliability. But for multi-state network reliability, this capacity related reliability has to be combined and has to be taken into the format, so that we are able to calculate the reliability. So for minimal path set approach, we try to get the capacity states of all the elements of the network, which are helping us to calculate to achieve the target flow requirement. So the capacity states of the network which contributes or which are successful from the network operation point of view, all those capacity states will be considered as a successful state. But what will happen, like these capacity states will be very, very high. So for minimal path set, we take the minimal capacity state. That means if I am having this capacity state as a lower boundary flow vector or minimal flow vector, then if any of these element is having a higher capacity than this or equal to the capacities like this, in all these cases the network will be successful, because higher capacity is not going to limit the flow. So DMP vector we get it. So we try to get all these such flow vectors, which we will be calling as a DMP flow vector, where D is the demand. So how much is the demand placed, and for that demand, what can be the minimal flow vectors which will meet the demand. Similarly, for DMC, it is the opposite. We take the upper boundary flow vector or the maximal flow vectors. So this is the flow vector which is having the highest capacity but not able to meet the demand requirement. So all these capacity vectors, so what will happen, either capacity is this or lesser than this for any of these elements, the network will not be able to meet the demand. So this will be called as a minimal cut set. So all such vectors are collected, and then from these we try to calculate the reliability. In like there are many work which has happened, like Lin, Zhou, Lin, and Ye, Chen. So they have all developed all these methods. So the general approach for calculation of reliability for these networks is, like, first we get the minimal path set. So minimal path sets means connectivity based. From this we try to find out the feasible flows using certain algorithms. So this gives us the DMPs for a demand D. From this feasible flows, we try to reduce it to a lower boundary flow vectors. So these lower boundary flow vectors finally set the way of calculating the reliability. Now these lower boundary flow vectors, they have the overlapping regions. Like if we say here, so one lower boundary flow vector LBF1, let us say, is this, LBF2 is this. So certain flow states will be part of both. So because of that, what happens, that when we calculate reliability, we have to remove this common part so that they becomes disjoint to each other, and we are able to add their probability to get the final probability value. So that becomes a challenging task for which we worked, and we developed some methods, and that I'll briefly discuss. Similar approach is for the minimal cut approach. For minimal cut approach, first we get the minimal cut, then we take the demand one less than the actual demand required. So all those flow vectors which will give one demand less than my desired demand, that is, all those flow vectors are not able to meet the my requirement from the networks. So therefore, all these will be considered as the cut sets. So from there, then we get the upper boundary flow. So out of all these flow vectors, we try to get the flow vectors which are the upper set of this. And from there, we can calculate the unreliability. So union of all this will give us the unreliability. And from unreliability, we can calculate the reliability as 1 minus unreliability. So all these, so there are methods available as cited already. So we can use these methods to get the flow vectors. And as we discussed, these flow vectors will have some common states. So these common states we need to remove so that we get a disjoint states, and once we sum the probability of these disjoint states, we will get the final reliability of the network. So earlier approaches which were used was like inclusion, exclusion, sum of disjoint product. So we have also developed a similar sum of disjoint product. I will present a simpler one, and then we have recently also developed a little more enhanced, more efficient approach which helps us to evaluate the reliability of such networks. Inclusion exclusion formula we already know, where if we have the 3 elements, we will have the 2 to the power 3 minus 1. That means around 7 combinations, individual, double combination and triple combinations. So odd number of combinations are joined by the plus sign, and even number of combinations, intersections are by the minus sign, and this is again odd. So here, once we do this, we will be able to calculate. But this process, when we see, if let us say there are 10, so we will have 2 to the power 10 minus 1 evaluations which we have to do. And because of that, as the number of flow vectors increases, this approach becomes non-tangible, and it can be used for a very, very small network like around 4 to 5 elements, not more than that. In SDP approach, we try to get the same expression, but in a little better way. What we do, we take the first flow vector combinations as it is. From the second, what we do, we remove so what we do here, if we have A and if we have B. So I'll take the A as it is, which is also taking the part of the B. But when I'm taking the B, I'm only taking the B which is intersected with A bar. That means that is having nothing common with the A. So essentially we are removing the states which are common with A. That if we take, that is the second. When we add C, then for C, I will remove all of its states which are common with A and B. And then whatever is remaining will be taken as the added states for this. So these approaches, some of these joint approaches, we have to apply recursively one by one. Like first we take this, then each and element when we do, we keep on removing the states from previous paths or previous flow vectors, and then we finally get the probability of expression which we use for the calculation. So here, like same thing, once we do, so we are able to get the final evaluation. If we look at the literature, then most of the existing algorithms are actually focused on DMP, DMC's generation more efficiently, but still they are not very efficient. We developed one more method for these evaluation, which helped us to do this even faster. And this inclusion exclusion doesn't help. This takes a lot of time and makes it impractical to even solve the small problems. So in this, when we develop this SDP approach, this we have taken the clue from the old papers given by Abraham, Hitman, Sohen Rai, Chaturvedi and Mishra. So these, we take a hint from there and we try to enhance this method so that we are able to apply on our networks. For the flow networks, we have already done for flow networks, but here we are trying to do it for the stochastic flow networks, multi-state flow networks. Okay. So let's take an example how it works. So that will bring a clarity to the listeners. Let's say if we have a network like this, which is a classical bridge network, where we have the 4 nodes S, T, and we have the 2 nodes in between, C7 and C8. And we have around 6 links here. C1 is here, C2 is here, then C3 is here, C4 is here, C5, C6. Now I want to transfer a demand from source to terminal. So first, before that, what we need, let's say we need to have these are my distributions. So each element is having a distribution. So if we see here, the capacity 0. Capacity 0 means complete failure for C1, element C1. This is this link. So that probability is 0.01. That means I'm having the link reliability almost 0.99, but that 0.99 is divided into multiple capacities. Like the capacity of link is 4, so 90% of the time it is going to stay there, but 5% it can have capacity 3, 2% capacity 2, 2% capacity 1, and 1% is the failure probability, complete failure. So similarly, we get the these discrete distributions for all the components. And now to evaluate this, first, as we discussed earlier, first step is to get the minimal path sets. So we get the minimal path set, like first path set is C1, C2, right? And in this C1, C2, this S and T always has to work. So we are not taking that into account because that is by default, they should be working always. If any of the S or T fails, then network will never communicate. So that is by default, we can multiply their probabilities at the end. So we need not to consider in our evaluation. Here if we see C1, C8, C2. C1, C8, C2 is one path. C5, C7, C6 is one path, right? So C1, C3, C7, C6, C6 is another path. So same way we get these 4 paths. One path is this, one is this, another is this, and another is this. So we get these 4 paths. Now, as we know these 4 paths, if I want to know only the connectivity, this information would have been sufficient to calculate the reliability. But from these, similarly, if I want to know the cut sets, I can have the cut sets from here. Cut sets means like if both of them fail, C1, C5, C2, C6, or C8, C7 fails. So similarly, we will get the cut sets here. So we have the algorithms for that and we can use it. From the path set, let's say my criteria is I want to have the capacity transfer. My requirement is that I should be able to transfer 7 units of the flow through this network from S to T. So for this now 7, how can I flow from here to here? Now if you see, my link capacities are maximum 4 and node capacities are maximum 6. So I have to make the combinations. So how these combinations will be there? So these combinations I am making like 4 paths are there. So this is path 1, this is path 2, path 3 and path 4. Like if path 3 passes the capacity 3 and path 4 passes the capacity 4, then in a way I will achieve the capacity 7. But here the problem is that path 3 and path 4 is having these 2 elements in common. These 2 elements are C7 and C8. So since these elements are common, for these elements, they have to transfer 3 also and they have to transfer 4 also. But their maximum capacity is 6. So because of that, this becomes an infeasible flow. And we have to drop that. So this way we make first flow combinations, and from the flow combinations, first we drop the invalid combinations where any link or node capacity will be violated. So this gives us the feasible flows. Once we have the feasible flows, now here feasible flows, once we have, we will get the capacity vector of the individual, which is quite simple. Whatever is the element, and for that element from that path, how much capacity is transferred, that will display. And wherever same element is being repeated in multiple paths, then whatever is the assigned capacity for that path, that will sum up. So this way, for all the 8 elements of our network, like these are the 8 elements of the network, we are having the capacity requirement which should be passed from this. So this gives us the minimal flow vectors, but this gives us the flow vectors which are feasible, but which is not necessarily the minimal. Why they are not minimal? Let's say if we compare these two. Here if we see, so minimal means we have to get the flow vectors, like if we see here 4, 3, 3, 2. So here if we see 2 is less than this, 1 is less than this, 3, 3, 4, 4, here 5 is less than this, while all others are either equal or equal to this, right? They are not higher than that. So as we see here, this vector is in a sense is a lower vector than this. That means if I take capacities this or higher than this is already accounted in this. So this becomes a redundant vector for us. So all these, so it's a very simple way. We find out the vectors which are minimal in nature. That means any other vector which is having a capacity equal or higher for all the elements for a vector, all those will be dropped. So this will be removed. In such a way, if we see all these 12 vectors are reduced to the 4 vectors only. Now these 4 vectors becomes our non-redundant lower boundary flow vector. From this non-redundant lower boundary flow vector, similar approach is for the TMC. Here the only thing is for D equal to 8, we will calculate the 7 capacity combinations, and from there we get the UBF. That means all the elements which are having flow less than equal to flow for any of these capacity element for in the vector, all those will be dropped. So we will take only the upper bound vectors. Now from this, like one approach which we developed, it's a simpler to understand. Algorithm is there. You can refer to the paper for more details. Here, if you see, let us say if we, the purpose of this like keynote lecture is to introduce you to this so that you are able to, if you are interested and if you get interested in this field, you can do further research in this. And here, like if you see this flow, 4 vectors were there, and for all 4 vectors, this is my upper boundary flow vector. That means the maximum capacities an element can have. Now here, there are 3 kind of conditions can come where that a vector becomes redundant. A vector will be redundant if it is having a capacity equal or lesser than another vector for all the elements. A vector will become disjoint with x1. That means those 2 vectors are not sharing any capacity states as a common state. Another possibility is that the 2 vectors have some common states. If that is the case, we have to apply this algorithm and we are able to reduce the states which are there as a common state. So let's see that how does it work. Let's say x, I hope I have time, right? I may take more than 5 or 10 more minutes, right? So if we have x1 here, so x1 will come as it is, as we have seen already in the formula. So x2 has to be made disjoint with x1. Now if we do that, then how do we do? We first see the capacity states in x1 which are lower than this for any element. So that means these capacity states, now what is happening, this is 3 to 4 and this is 4 to 4, this is 1 to 4, this is 4 to 4. So since this is 3 to 4, that means it is having some states which are common with this. So all these states now, so here we are having the 3 elements for which capacity is smaller than the capacity of x1. So these states are having a possibility of states which are having some common states with them. So if we work on this, we are able to reduce them. So for that we do this analysis. So in this case, let's say we take one element one time. So what happens, this 4 which we have 4, this is my x1. So my x2 is from 3 to 4. Now 3 to 4 I am having, so I am dividing in 2 parts, 3 to 3 and then 4 to 4, right? And rest of the things are same. So when I make 3 to 3, it becomes disjoint with this, because now it is not, for this element, it is not having any common state with the x1. So this becomes my disjoint element and the probability becomes additive to this. Now the second part, if we see, the 4 to 4 is part of this. So this becomes as it is. Now I take the second element 0. Now if you see 0 here, this is 1 here. So that means I have to make it in 2 parts, 0 to 0 and 1 to 4. So this becomes 2 parts, 0 to 0 and 1 to 4. Once we do that, then 0 to 0 becomes again a disjoint part with this. They do not have any capacity state in common. But this 1 to 4 is again becoming same. This is becoming similar to this. So this all becoming part of this. Now only part which is remaining is here, 3 to 4. Now 3 to 4, if we see here, 4 to 4. So again we divide this into part 3 to 3 and 4 to 4. Now this 4 to 4, if we see, now this part we have is actually already part of this, because this is a subset of this x1. So this we have to draw. So as we see here, we had the 3 elements. So for 3 elements, we generate 3 combinations of x2. So all these combinations are listed here. So we have the lower boundary to upper boundary for all these 3 combinations. So this becomes the answer. And for all these combinations, once we calculate the probability and we sum it up, that gives us the reliability of x1 and then x1 union x2. So same way we do it for the x3. For x3, I would like to see first step is same, x1 bar x3 we calculate, and once we do it for x2 bar, then we compare the same with x2 bar. Here what happens, this third state which we have is already disjoint with x3. This is not having, because if you see this is 3 to 3, but this is 4 to 4, 4 to 6. So they do not have any state in common. So that means they are already disjoint. So LB3 did not to be changed, but others again get modified, and again using the similar process we get the again set of the vectors from lower boundary to upper boundary. So it generates like 1, 2, 3, 4, 5, 6 and 7, 8, around 8 vectors we get generated from here. Similarly, this process continues and we are able to calculate for all the vectors. So finally we get for x4 also, and total number of disjointed flow vectors are 18 for all this problem, and once we calculate the network reliability, that comes out to be 0.743. This is after following this distribution. So this method has been published and long back. Now we have also modified this to consider the where the joint this multiple inversion is done. So that is further enhance this approach into more efficiency. By efficiency improvement here, it is necessary to consider, because these problems were earlier. Yes, please.
Please conclude in 5 minutes.
Yes, I'll take around 3 to 4 minutes. Yeah. So what happens in general, like when these methods, for using these methods in practical sense, they have to be efficient. Because of the inefficiency, what happens, we are not able to solve the problems. But with this improvement in efficiency, now we can actually solve the bigger networks. As you see that for all these networks we have considered, and we could calculate the reliability which was earlier not possible. And for all these results are given, and we have verified the results with earlier methods and doing the calculations, and once we find out that reliability values were same, and but efficiency was quite high. Like if we see here for demand 5 units, we have considered various networks, how many lower boundary points were generated, how much was the reliability, how much is unreliability, what was the time taken when recursive SDP was used, when ISTP was used, and how much was the time when we did this method. So once we use these methods, this was further enhanced, as I told, and the that further reduction in time was there. That was almost like 10 to 100 times. So this more efficient and higher methods helps us to calculate and solve the practical problems. So we hope that in future we will be able to like solve practical problems. Like let us say if I take the like whenever I visit Bangalore, we see a lot of traffic issues and all those. So these kind of approaches can help us to solve many practical problems. But till now we have suggested the theoretical problems, but there is a lot of future scope available in applying these methods for the practical problem solving, because all these networks can be modeled using these flow networks, and once we model it, if we use these computational methods, that can guide us to find out the exact places where we should be able to focus to improve, so that we are able to remove the bottlenecks, or we are able to design the alternate flows, and because of that our traffic requirements are being met in a more reliable manner. So in this case, like many times people use multiple attributes, budget constraint, all those things can be done. But I would request, if anyone is interested to take this further for practical problem solution, that will be great, because that is what our country needs, and we can definitely have a larger contribution to the our nation and the society in general. And so with this, like this is some references which I've used in this presentation are given here. So that's all from me. Thank you for your patient listening, and I'll request, if you have any queries or any suggestions, all are welcome.
Yeah, any question from the audience, please?
Professor Goyal.
Sir, yeah, but this is a good afternoon, sir.
Not able to see, but people want you to see me actually. You are. वैसे हम परसों मिलने वाले हैं.
Yes, sir. Yes, sir. We'll be meeting. Yes, sir. I'll be there.
But I am happy that I craved for such things. You know that.
Yes, sir.
Was showing one application-oriented development.
Yes, sir.
I don't have any comment, but मुझे ऐसा लगता है कि how you will do testing and validation the model that we have developed, maybe उसके बाद you will have more robustness and probably reliability of this thing. No, they allow you to do, like, you know, if you take some hardware component, their characteristic, so probably we should be very having a robust input for that, because that is going into our model, you know. So
yes, sir.
And our model itself, like this model, even if you write a program or something, it should be robust enough. So that is my comment, and I think you have done a wonderful job. Maybe some feedback also come once you put it in practical uses.
True, sir.
The last slide, future direction. I think you are indirectly you are inviting people to take part into, or support this or add it to some element. So
yes, sir.
Welcome. Thank you so much.
Thank you, sir.
As soon as I go from here and day later, I'll be meeting you then.
Okay? Sure, sir. Thank you, sir. Thank you.
So morning you come early because I have to distribute the certificate. I've been called there.
Yes, sir. I'll be reaching Sunday because I have my parents are there, so I have to meet them also.
Thank you, sir.
Yes.
Yeah, thank you, Dr. Neeraj. Any other question? Yeah, thank you, Dr. Neeraj.
Thank you.
Professor Dheeraj, how your parents thought that you will have a lot of patience, Dheeraj? You were patiently sitting there, listening. I appreciate. You have done a wonderful job. Because I became impatient. I told the, she in very. But at the outset, I think your name is suiting your personality actually. You have a lot of Dheeraj, So I think I from the Professor Kapoor's behalf and his, INBUSH and ICRT MB चलेगा खत्म हो रहा है ना अभी तो. So thank you so much. Thank you so much and for supporting this initiative. And I think the Kapoor sir will give some honor. Yes, sir.
So thank you so much, sir, for this insightful presentation. Now I request Professor P.K. Kapoor, sir, Dr. Anil Bhutani, sir, and Professor Prabhakar B. Verde, sir, to felicitate our session chair, Professor Dheeraj Pawar, sir.
Okay, so all the sessions are over. Thank you so much for all the patience. You may all proceed for the lunch.
Thank you so much, everyone, for joining us.